All right, we have our second panel on synchronous versus asynchronous composability. So Justin, I think you're on this panel again. And we have Porter from ZK Sync, we have Yi from Scroll, we have Bryan, and we have Jordi. Is Bryan Pellegrino here? Oh. Yeah. It's okay. All right, we can get started, and Bryan will join us. If somebody can go find Bryan, that would be great. I think Bryan might be in the speaker room, so. Okay, so why don't we start out, since this is about synchronous versus asynchronous composability, I don't know that everyone has sort of the same idea of what synchronous composability exactly means. What is the difference between synchronous and asynchronous? And so does one of you want to first take a stab, and then if some of you disagree, we can have two definitions? I don't want to turn the whole panel into a definitional debate, but let's sort of set some common ground here so that we are on the same page before we begin discussing at length. Is your mic on? Just flip the switch.
I'll use this one.
Okay, perfect.
Okay, so a definition of synchronous composability. One way to define it is that it's the exact same composability as the L1 today. So if you have an L1 contract and another L1 contract, they can compose synchronously with each other. What does it mean? It means that you can make a call from contract A to contract B, and you get a response immediately. And not only can you do like this message passing of like request response, but you can also do immediate asset passing in and out. And so synchronous composability is about extending this superpower that we have at L1 to contracts across rollups. So you have contract A on rollup A, contract B on rollup B, and you want to have the exact same kind of composability. And the two big requirements in order to get that kind of really luxurious composability is one, shared sequencing, and two, real-time settlement.
Do you all generally agree with that distinction, or does anyone want to offer? All good. Bryan, we've just started with talking about asynchronous versus synchronous composability, sort of setting the ground for what people really mean when they talk about synchronous versus asynchronous. So, Jordi, Yi, or Bryan, or Porter, do you generally agree with Justin's distinction?
I think is a lot of. Well, obviously, composability is super important, and we do want composability, and I think a few of the points are just like good composability points, but they're not necessarily like asynchronous composability can still maybe be very, very good, because I don't know if there are actually that many places or times where you really need the synchronous part of the synchronous composability. So I think maybe everyone on the panel probably agrees on composability is important, and then how we get there is probably where there are more differences.
Yeah, I mean, and that's going to be the point of this panel here, is to talk about the advantages or disadvantages of each. But right now, we're just trying to get on the same page of what is asynchronous versus synchronous. Sometimes I hear people confuse, atomic execution, synchronous composability. So there's atomic execution is something people talk about. People also talk about synchronous composability. Is there a difference between atomic execution and synchronous composability? Is atomic execution a special case of synchronous composability?
I mean, going back to the definition of the words, like atomic means that you can't break it down, and so atomic execution means that you have two transactions that are both executing at the same time, or none of them are executing. With synchronous composability, you have something slightly different, which is that you have the ability to read and write state immediately and pass assets in and out. Now, it turns out that you can get the atomicity safety guarantees using things like AgLayer, using SNARKs. And so they're like slightly different concepts. One is like a safety guarantee, and the other one is a composability guarantee.
So one way that I like to think about it is through function calls between smart contracts. I would say, so an example of atomic execution is a user wants to execute transaction A on chain A and transaction B on chain B, and you can have a mechanism which gives them a guarantee that both of those transactions execute either together or succeed either together or not at all, and that would be atomicity. But that's not necessarily the same as function calls between smart contracts, where you have a transaction that initiates a message to another contract that then takes some actions, and based on the results of those actions, gets a message back and does something else, right? And that's something that we can do between contracts on Ethereum today. That's one of the hallmark properties of Ethereum. You can have an application make a function call to another application, wait for a result before doing something else. And that's different from, that's a form of atomicity, but it's beyond basic atomicity.
You can solve atomicity at more higher level. I mean, if you have an asynchronous system, of course, it's not straightforward. It's not out of the box as it would be in a synchronous system, but I can build a smart contract that works in a synchronous way. I mean, asynchronous calling, I mean, just message passing, some sort of timeout. I mean, if this transaction doesn't proceed, then you just roll back the system. I mean, you can build some systems in an asynchronous way. So atomic transactions are possible, and here the difference is, do we want to be natural, I mean, in a synchronous way, which simplifies the things very much from the user perspective, but gets the things much more difficult and much more complex at infrastructure level, and with some doubts on how scalable and what are the setups on that, or do we want an asynchronous system, so kind of asynchronous calls between the chains, and then you can build this atomicity or this tooling or this this layer on top of that guarantees to the user, and this gives the user the tooling for working with this multi-layer synchronous, something that somehow simulates or emulates or looks like a synchronous calling. I think this is the big debate that there is right now, and here there is like advantages and disadvantages of trying to do one way or the other.
So Jordi, just to make sure we understand, so are you suggesting that something like function calls between smart contracts, where let's take the example of a flash loan, right? Contract one initiates a loan, right? This enables some kind of function call to another smart contract that executes a swap, et cetera. You're suggesting that any time you have synchronous composability of this form, you can emulate that through asynchronous message passing? Is that what you're suggesting?
You can. I mean, what I'm suggesting is that all applications can be built with an asynchronous system. So there is no application. I mean, you can build atomic transactions with. Other thing is the difficulty, the friction for the user. Okay, because I mean, you need to think about these asynchronous things and what happens when there is transactions that are in the middle, and how they roll back, and how the things work, and how you isolate that from the user perspective. But you can build that. I mean, it's not that if it's a synchronous system, you cannot build an atomic transaction system. You can definitely.
Right. So you're characterizing the main difference in terms of just time, right? It sounds like, because you're saying that the difference between in a what we're usually calling a synchronous system, you have an application make a function call to another application and wait for a response. You can do that through message passing, where an application enters an intermediary state, sends a message, and then once it gets the message back, it can decide how to enter a new state. And so you just have these intermediary states. And so you're saying that one characterization of the difference between synchronous versus asynchronous is really just on time. And is that fair? Is that what you're characterizing here?
Well, it's time and how you are building that. It makes a lot of difference. If you have to build a smart contract that have asynchronous calls, from the smart contract perspective, is quite different. Other thing is that you have some library or something on top of that that somehow helps.
Difficulty for the developer.
Exactly.
Right.
So you help to the user just because you are somehow hiding or abstracting or black boxing this functionality to the user. But it's not as a strike. It's not as a straightforward as the other thing. You design the system that's synchronous, and then it's okay. It's the same that you had before, and now it's synchronous.
Right.
Here we can talk and we can discuss the advantages or disadvantages. I think that these synchronous systems are, if you are trying to build from scratch, if you are not isolating that part, I think it's much more difficult to build, and it's more, I have a lot of concerns about the performance, and in general, what I see is, for example, just go to the internet part. Internet is synchronous or asynchronous. we love synchronous. Actually, if the people that came from the beginning, there were a lot of good synchronous protocols for talking about internet. RPC, Unix RPC, not the JSON RPC, just the Unix RPC was the first example and this didn't succeed in the internet because there were problems. Maybe sometimes the other part of is not responding or is just delaying, or there is things that can happen in the thing. But there are others. Microsoft had one thing that was called DCOM that didn't work in the internet context. It worked very well when you control both sides of the communication part. But if you are talking with something that's very different, that is untrusted part, then things are quite difficult. There is other things like Corba. I don't know if people remember about that. And everything went to, so the travel, the trip was, let's go to synchronous here, then good things that starts working with this, how is called this asynchronous call from the browser at the beginning, and then end up in these JSON RPCs, which are very much synchronous. But again, we then with that working and with that in place, then we wrote the right libraries for the user to have the feeling that they are working as synchronous, and they have to not worry very much about that, because all these timeout handling, all these rollbacks, all this problematic is quite transparent from the user. I think this is a better approach, but again, here it's not that I am all in on that. It's interesting to see what the people think, and see how the systems evolves, and understanding very well what are the advantages and disadvantages.
Yeah, so let's segue into looking at what people here see as the advantages let's start with advantages, okay? So let's look at what we think are the positives of having synchronous composability. And so this now means either, so we're talking in a cross-chain setting, right? Because we have synchronous composability within individual chains. So we're in a cross-chain setting.
For most VMs, not all.
What?
I said for most VMs, not all. We're getting to the world where we have a bunch of async VMs now too.
I see. Okay. Well, we're in a cross-chain setting, right? So let's focus on in the cross-chain setting what each of you think of as the key advantages of synchronous composability. And one way to approach this is saying, here's an application that that really relies on this. Flash loans are the example people give all the time, but I'd love to hear examples beyond flash loans. And Justin, in your talk this morning, you had like 14 different things. I'm not sure if they were all exactly examples of this of synchrony versus asynchrony, but you can choose to highlight maybe one or two. So why don't we just go down the line? So maybe starting with Porter.
Yeah, I'm not sure there are actually that many times where you need like synchrony across chains. I'll use like an example. Like any application is almost always built just for the one place, and then like Uniswap will just deploy multiple contracts across everyone. And like theoretically, you could get like better shared liquidity if you had like completely unified across all the chains. But the liquidity is already like quite good on most of the L2s. And so there aren't too many times where like an average user wants to go across. So like we need to just like consider like what situations are there that actually require the synchronous composability cross chain, and I don't think there are like that many besides like MEV.
Even if you're focusing within one chain, right? You can ask the same question about applications. So are there any applications, let's say on Ethereum, where the fact that Ethereum applications are able to synchronously interact, which is arguably one of the key advantages of Ethereum over other systems, over Web 2 systems, right? You're saying there may not be many. Is there any that you have in mind, let's say beyond a flash loan, that takes advantage of the ability of applications to synchronously interact?
Maybe like, I don't know, generally like library calls and stuff, but like a lot of things that, it's fine if it happens like, transactions a couple spread apart. I don't know too many cases where, if someone else has ideas, they're welcome to.
Right. Okay. Justin?
I think there's a lot of applications. One of them I talked about is this idea of liquidation, right? Like, if I want to build something like Aave, I want the ability to liquidate immediately and not take on some sort of price risk with some uncertain execution that happens asynchronously. There's also the loan refinancing, which is one of the use cases for flash loans, right? Like, let's say I have 100 ETH, I've taken some DAI loan, and then the DAI rate kind of goes too high, and I want to go to liquidity, for example, and I've already spent the DAI on something else, on a car or something. The flash loan can do that. Without the flash loan, you have to go in and out like 100 times. It would be extremely inefficient. But even for simple transfers, there's this notion that I want to make a simple payment. I want to buy an NFT, and I don't know what the gas price will be in the future, but I do know what the gas price is in the present, and so like these little things kind of can significantly affect user experience. And then another thing that I highlighted is pre-confirmations, right? So if we have, let's say, a 1 second slot time, and we have an asynchronous super transaction that takes 3 different slots, that's going to take 3 seconds. If it all happens in one slot, not only is it like 1 second kind of next slot settlement, but you get even more than, you get better than that. You get a pre-confirmation from a single counterparty within 100 milliseconds, and so the difference between 3 seconds and 100 milliseconds is massive. And then kind of putting your imagination hat on and try and project, okay, what will Ethereum be in 10 years time or in 5 years time? We're going to be building like hyper complicated like superstructures. Because right now, we're building Lego blocks. We're building transfers, swaps, loans, like little things, ENS. But eventually, we'll start taking these Lego blocks and building castles. And then these castles, if they're all like, all the Lego blocks are asynchronously connected to each other, it's going to be like building on sand. It's going to be very weak. And so I think the more complex the applications become, the higher the need for synchrony will be.
Bryan.
It's interesting. I almost have a completely agree with so much of that and have a different conclusion, which is very interesting. I think when you're talking what are the benefits of synchronicity in general, it's basically how much does latency from the time time of the event until the execution of whatever you're trying to do, like how much does latency affect it there? So this is why like flash loans is obviously like the canonical example, but there's a ton of other things, even as Justin is talking about, right? Like where is gas priced, right? Like some event happens now, I want to execute this thing right now. Well, doing that and having a bunch of other things between something happening and my thing being executed is just very different. But I think the nature is like async is a necessary evil. We talked Jordi talking earlier. There's a ton of like. I also agree with a lot of what you were trying to say, Jordi, but I think there's so much like hand waving of stuff that needs to get done to even get close to getting that future. It's like, okay, like, don't even start thinking about what happens of rollback risks for any of the chains. And then if you have some layer to do that, like now, what are the sacrifices all of those chains are making to be able to, there's just like so much that goes into that we're not even close to getting there. I think if it looks anything like how a bunch of web and other stuff is developed, like we will be many series of many async calls, and like we will have to develop applications in that manner. So I agree a lot with the benefits of what you're saying for like smaller subsystems, but I think the end state when you talk complex systems at scale will have to be many series of async calls, which is my like natural assumption. But I'm curious I'm curious in a world where that doesn't need to exist, I guess, is what I would say.
One thing that, just to distinguish the thing, sometimes we are talking or we think on our mind that synchronous is faster than asynchronous. And I think latency and synchronous and asynchronous, it may be true in some cases, but it's not, there are two things. I mean, maybe an asynchronous system can be even faster than a synchronous one. I mean, maybe asynchronous, you're waiting for two parties to find the right slot and you don't find it.
For sure, the assumption is nothing else can happen in between, right? Like,
so it's not clear. So just to be clear, I mean, it's not clear that synchronous, from the user perspective, synchronous is going to be faster than asynchronous. What's clear is that from the user, from the developer perspective, working with asynchronous systems is harder than working with synchronous systems. So for me, the biggest advantage of asynchronous systems is that, I mean, it's transparent from the developer. If you know how to build smart contracts in Ethereum, you know how to build cross-chain smart contracts. And this is the big advantage, and this is the big thing from the synchronous part. Besides that, I mean, this is huge, but besides that, everything else is problematic. Okay? And it's hard, and it's difficult part. So here my proposal is more, okay, let's start with asynchronous, which is easier. I mean, from the infrastructure perspective, is easier. It's, I would say, faster to develop. We can start experience with that. And then we can build synchronous systems on top of that. But my concern is that but again, I mean, this is it's an opinion. My concern is that we are trying to build synchronous system from the beginning with all the difficulties that it has. Maybe we are going to go slower, trying to go faster.
I see Justin ready to jump in here, but we've skipped over Yi for for advantages of. So do you think you can hold that thought, Justin? And then we're gonna have to wrap soon, anyways. But I want to get back to you. But Yi, what? Sorry for skipping.
Yeah. I agree with like what you mentioned. All the application side, the liquidity. I guess difference is actually the implementation problem we actually need to consider, because there are a lot of like theoretical work of like how great data is, but from a very concrete like system perspective, I'm being very honest. Like I think first thing like a layer 2 need to do is that firstly getting your chain like running like in a very robust way, running in a very stable way, and then talking about like two chain having synchronous compatibility. Because from system perspective, your system might, especially with the scale increasing, synchronous compatibility can get very, very complicated to build.
I mean, we've all talked a lot about sort of the complications to developers, but the thing I really wanted to focus on is what are the advantages? Because if the North Star is synchronicity, what are actually the applications that take advantage of it? I mean, what's an application on the L2 that you think would be really unlocked by having more synchronous?
So I think the flash line liquidation is the best example still. I'm thinking like, I think it's in some sense, if the system can handle the synchronous stuff from the infra side very well, it's still good for developer, because you can basically, like in synchronous model, you can access the state of all the rollup almost like equivalently, because you can program over any state and you can access, you can do contract call over any state, any libraries, and doing anything like that. But in a synchronous case, you need to like consider that the state when you are calling that is not there yet. So if you trust the system can handle that well, I think that's still good for developer experience, because you are basically programming over just one chain over the same state and infinite state, every chain state you can directly access. But only if like your system handle that well. I think that's maybe like one advantage for synchronous compatibility. If Yeah.
So again, it sounds like your conclusion is it's not a specific application, but it's more the developer experience. It's easier to think about a synchronous system.
Yeah, because you can access any state basically.
Justin, do you want to respond to Jordi? It sounds like you were.
Yeah, I mean, one of the fundamental things is that you can't build synchrony on top of asynchrony, but you can build asynchronony on top of synchrony. And so, like, if you want to be maximally forward compatible, your foundation needs to be synchronous. Now, the thing is that synchronous doesn't mean that you have to buy into the synchrony all the time. You can have this notion of optional synchrony, like, pay-as-you-go kind of thing. Like a user really wants synchrony for like this piece of state. They buy a lock, and then they get monopoly access for some period of time. But by default, what you could totally have is like parallel execution of transactions with zero synchronous composability. So I think it is important that we have strong foundations with shared sequencing that give you the option in the future, if you do want to have synchrony, the option for users to pay for that. Now, one of the things that you said, Jordi, is that synchronous is not necessarily faster. And I think there's like two notions of fast in the system. There's latency and there's throughput. And really what synchrony is all about is trading off throughput for latency. So you have the lower latency, but because you're locking and you're blocking the system, you're limiting the throughput. And so in some sense, it's about
so when you say throughput, I mean, you mean like other actions that happen, and you don't necessarily mean, throughput's usually a measure for how many transactions can get through per second. So what do you mean by throughput here?
Yeah,
do you mean
transactions per second. Like in the like extreme case, like I buy a lock for the whole rollup states, and then I block everyone, and no one else can execute, and only my transaction goes through.
Right.
And you have like a really valuable, like high quality, like low latency transaction that you want to push through, and you're willing to pay for it, but you'd have to outbid the totality of all the fees from all the other users in order to do that. But also, like the most simple way to like bootstrap the system is to have no synchrony, just let everything run in parallel, but with a centralized sequencer, a shared sequencer in case you do want synchrony in the future.
Is it fair to say that in a system where an application is able to, it's behaving synchronously, even if it's, let's say, taking a long time, but if an application makes some kind of call to another application and then waits for a response, there isn't a lot of other things that can happen in the system. So we're kind of measuring time by number of things happening in the system, number of changes of the state that happen between when the beginning of an action starts and when it's supposed to end. In a synchronous system, you can really limit the number of other interactions that happen between those two times. Whereas in an asynchronous system, there's a lot of unpredictable stuff that could happen. It doesn't matter the time over which it happens, it just matters how much happens, how much changes the state, and that leads to uncertainty. Right? Okay, great. Well, we're moving on with our agenda, so thank our panelists here.